So now we're going to be looking at practice test 7, passage number 5. And we know it's passage number 5, so we know it's a science passage. But lucky for us, we don't actually need to have any knowledge about science. It's more about reading comprehension and our skills in that department. So we're going to really focus on making sure we understand the passage by going through and making a roadmap. And we're going to do that because when we go to the questions, we're going to need to look back to the passage. And having a roadmap is going to save us a lot of time because it's going to tell us where we need to look. So we're going to start here in this passage with their blurb up here. I'm just going to take a quick look at it because it's going to contextualize us, tell us what's going on. So the passage is adapted from Brian Greene, How the Higgs Boson Was Found, 2013. So that's How the Higgs Boson Was Found. Probably important title. Copyright 2013 by the Smithsonian Institution. The Higgs boson is an elementary particle, associated elementary particle. That seems, okay, we know what it is. Associated with the Higgs field, proper noun. Those seem like things we're going to want to keep track of. Experiments conducted in 2012 to 2013, time, always a good thing to keep track of. Let me get a little space there. Tentatively confirmed the existence of the Higgs boson and thus the Higgs field. So we see the Higgs field twice. Going to keep track of that. We got this 2012, 2013, and the Higgs boson. Great. Now we're going to dive into the actual passage. Nearly half a century ago, right off the bat, we have something telling us when we are. That's going to contextualize us. It's going to allow us to move through time in the passage. We can know further sooner. Nearly half a century ago. Important. Peter Higgs, proper noun, someone we're going to keep track of, and a handful of other physicists were trying to understand the origin of a basic physical feature, mass. So you know that they're looking for mass. Great. That's important. You can think of a mass, blah, 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 blah. We have more information about mass. And then it says, but where did these masses come from, right? Where did the masses of these and other fundamental particles come from? So looking for mass, right? Higgs is looking for mass. We don't need to know about the minutiae of what mass is. This is what we need to know for now for this read. Higgs studying mass. Great. Okay. When physicists in the 1960s, more time, about the same time, so we're going to want to keep track of that. We're kind of in the same time in this paragraph here. Modeled the behavior, blah, 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 blah. If they imagined that the particles were all massless, then each term in the equations clicked into a perfectly symmetric pattern, like the tips of a perfect snowflake. A lot of perfects there. Great. So we know if they imagine them massless, they're going to click into a perfectly symmetric pattern. So massless is good. Okay. But, transition word telling us contrast. And here's the puzzle. They knew they did have mass, but when they put in the mass, the equations became complex and unwieldy and were still inconsistent. They were spoiled. So we're going to say here, mass-spoiled equations. We don't need to know really why that is, but it's important that we know that that's what's happening. That's the main idea of this paragraph. Great. So what to do? Higgs. Here's our friend Higgs again. Instead, keep the equations symmetric. Consider them operating in a peculiar environment, okay? Oh, now we hear the Higgs field. Imagine that all of the space is uniformly filled with an invisible substance that exerts a drag force. Blah, 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 blah. Great. Interpret the resistance as the particle's mass. Great. And then they give us a good example of like this ping pong ball telling us more about it. Its interaction with the watery environment has the effect of endowing it with mass, so the particle is submerged in the Higgs field. Can't speak today. So now we're going to say mass because of the Higgs field, right? The Higgs field is making it seem like it has mass, even though it might not. Great. Moving on. 1964. Still in the 60s. Important to keep track of. Higgs submitted a paper, but it was rejected. Not because it contained a technical error, so wasn't anything wrong with it, but because it seemed like heaps of overwrought speculation. That seems like a big, important extreme to keep track of. This extreme language is going to be really important in figuring out main ideas and determining what's happening in the passage. Great. So, no obvious relevance to physics. That's harsh. Say Higgs rejected. Put a little exclamation point at the end, a little spice there. But Higgs persevered, kept going. Blah, blah, blah. They had gradually realized that his idea was a stroke of genius and blah, blah, blah. Great. more explaining of what the Higgs field is. That's going to be our main idea there, just that line, because it tells us exactly what we need to know. Okay, great, now we have this like shift of third person to first person. So what's happening in this paragraph? We got to figure that out. Happened in 1964, proposal in 1964. By the mid-1980s, different time period here, the assessment had changed. The physics community had, for the most part, fully bought into the idea that there was a Higgs field. In fact, I had no idea it had yet to be established experimentally. And basically what he's saying here is that mathematical equations become entrenched in the vernacular of working physics even before there's data to confirm them. Doesn't matter if you don't know what vernacular means. It doesn't matter if you don't know what unwieldy means. What's important here is that this idea that Higgs proposed is being accepted. So concept taught with certainty. We could say like hypotheses, because we want to make sure that, hypotheses. We know that it's not confirmed. It's not been experimentally confirmed. Great. Now we're going to keep going to see if there's more information on the next page before we get to the questions. Oh, and there is. We have this nice graph that I've marked up a little bit already. So years from introduction of concept of particle to experimental confirmation. Right. We know from the passage that this Higgs field, for example, was proposed in the 60s, like 1964, and it was accepted around 2012, 2013. And this graph is telling us exactly that. We see this time period here. And it also gives us some other different particles that are, have some time between the year that they're introduced to the year that they're actually experimentally confirmed. Cool. Now we're going to dive right into the questions.